You could even use it as a verb if you wanted to, as in, I gotta go TBAF this alcohol after lunch. In this video, we're going to talk about the concept of protecting groups. What are they? How do we use them? And what do we do with them in organic chemistry? To start, let's look at this reaction that we have here on the screen. We have this reaction. We're going to take the starting material, react it with sodium amide and ethyl bromide. And if we look at the product that's formed, there's a problem. This is not actually the product that we would make if we took this starting material and subjected it to these conditions. These reaction conditions would not form this product. What would we actually form? If we actually took that starting material and reacted it under these conditions, we would form this product. The ethyl group would get attached to the oxygen, not to the alkyne. That's kind of a problem. If I want this product, I can't make it using these reaction conditions because it would make this other product. Let's figure out why, and let's see how we can use protecting groups to solve this problem. The problem is that this molecule has two different acidic hydrogens. We have the alkyne acidic hydrogen, that's the one we were trying to remove with our base. That has a pKa of about 25 or so. But the alcohol hydrogen is also itself acidic, and it has a pKa of around 16 or so. Of these two, the alcohol is by far the more acidic proton. When this base gets added then, the base will react with whatever's faster and easier, and the faster, easier thing to remove is the most acidic proton. The most acidic proton is always the most reactive in the molecule. So this base will react with the alcohol proton instead of the alkyne proton. We'll make an O- alkoxide anion. That alkoxide anion will react with the ethyl bromide to form the ether rather than the alkyne addition product. That's really a problem. But we can use this concept of protecting groups to solve that problem. The problem that we're trying to solve with protecting groups is the reactivity of this alcohol. This alcohol has an acidic proton. We need to somehow mask the reactivity of that acidic proton so that it's no longer in the way. Then we could add our base to remove the proton that we want to do the reaction that we want. We want to be able to mask that functionality in order to do this reaction. But we only want to mask it temporarily. We want to be able to unmask that alcohol later on so that we can have the alcohol back so we can form the product that we want. This is the concept of protecting groups. They are a functional group that mask the reactivity of an undesirable functional group temporarily so that we can do whatever we want to do. And then later we can remove that protecting group to restore the functional group back to its original condition. There are lots of functional groups. I have a book in my office of protecting groups for a variety of functional groups. We're only going to learn two protecting groups in this course. One for alcohols, and one in a separate video for carbonyls, for aldehydes and ketones. In this video, we're only going to talk about protecting groups for alcohols. And the protecting group that we're going to learn is something called a silyl ether. A silyl ether can be used as a protecting group for alcohols. If we consider a traditional ether is an oxygen with two carbon groups on either side. A silyl ether is an oxygen with an alkyl group on one side and a silyl group on the other side. Silicon with three other alkyl groups attached. Silicon is right underneath carbon on the periodic table, so it also makes 4 bonds. 1 bond to oxygen and 3 bonds to something else. This is a silyl ether. It is very structurally similar to a traditional ether. Traditional ethers are fairly unreactive. They are resistant to most reagents. Silyl ethers are also resistant to most reagents. So we're going to learn a silyl ether protecting group strategy to accomplish the goal that we want to accomplish. We're going to actually pause here for a moment. We're going to switch over and we're going to learn how to put on silyl ether protecting groups and take them off. And then later we'll come back and we'll figure out how to do this reaction in order to produce the product that we want. So I'll see you in a little bit. Okay. Let's step aside for a moment and learn how to put protecting groups on and take them back off. Our net reaction for putting a silyl ether protecting group on is going to be some kind of alcohol reacting with some kind of trialkyl silyl chloride and pyridine to form the silyl ether protecting group. Some notes for this reaction. The R group on the silicon, the 3 R groups, can really be any alkyl group. Could be trimethyl silyl chloride, triethyl silyl chloride. Even there are some exotic ones with 2 methyl groups and a T-butyl group. It really doesn't matter what the 3 R groups are. That's not what we're focused on. That's not the important part. Pyridine is a proton sponge. So we use pyridine here to sop up acidic protons. We could also use triethylamine. Those are fairly interchangeable. And again, our goal for silyl ethers is that silyl ethers are inert to most reagents, say strong bases, so that they can be in our molecule and not react in a way that we don't want them to. So let's go through a mechanism for the protection of an alcohol to putting on a silyl ether protecting group. We'll start with an alcohol and we'll react it with, we'll say triethyl silyl chloride. Again, those 3 R groups are irrelevant. So triethyl silyl chloride has a silicon chlorine bond. Again, silicon is just below carbon in the periodic table, so it has similar properties, similar reactivity. The alcohol can attack the silicon and kick out the chloride in an SN2-like reaction. That will form a new oxygen-silicon bond, and we still have 3 ethyl groups attached. We still have the hydrogen attached to the oxygen. We don't have any arrows showing the loss of that hydrogen, so the hydrogen is still there, and now oxygen has a positive charge. Pyridine then will act as our proton sponge to sop up the acidic hydrogen, neutralizing the alcohol and forming our protected alcohol product. This is now the protected alcohol. Notice that it does not have an OH bond anymore. It is not acidic. It does not have an acidic hydrogen. So it will be inert to bases, and so we can do things that we otherwise would not be able to do with the alcohol in place. Now that we have the protecting group in place, let's learn how to take it off. We take off the protecting group with a reagent called tetrabutyl ammonium fluoride. 4 butyl groups around a nitrogen with the fluoride counter anion in water as a solvent. That deprotects the silyl ether and forms and reforms our alcohol functional group. The reason that this reaction works is we're going to form a silicon fluoride bond in the byproduct, and that silicon fluoride bond is one of the strongest sigma bonds that we know. Tetrabutyl ammonium fluoride often goes by the acronym TBAF, TBAF, and TBAF is it's kind of a fun word to say, and you could even use it as a verb if you wanted to, as in I got to go TBAF this alcohol after lunch. So TBAF, you may also see that acronym in place of tetrabutyl ammonium fluoride, but they mean the same thing. Let's look at the mechanism for the deprotection reaction. If we start with our protected alcohol, we can add TBAF in water. TBAF, if we look at the structure of tetrabutyl ammonium fluoride, it is a quaternary ammonium salt, so it is a nitrogen with 4 butyl groups attached. That gives nitrogen a positive charge, and fluoride is the counter anion to that nitrogen. The fluoride is what's important in this mechanism. We use a lone pair on fluorine to form the strong silicon fluoride bond that forms an alkoxide, and that alkoxide can get protonated by water to reform our alcohol. And the byproduct here is the silicon fluoride, and that is the thermodynamic sink. That's the driving force for this reaction. Now that we've seen how to put on and take off the silyl ether protecting group, let's go back to our original problem and see how we can solve that problem using this protecting group strategy. Okay, now that we've learned how to put on and take off silyl ether protecting groups, we can figure out how to do this synthesis the way that we want to in order to produce the product that we want to. Again, we have 2 acidic protons. The problem is the alcohol proton is the more reactive one. So to do this synthesis, first we're going to need to protect the alcohol as the silyl ether. I'll choose the triethyl chloride and our proton sponge pyridine. That will protect the alcohol as the silyl ether. Now we no longer have that acidic proton. The functional group is not in the way. Now we can do our alkylation reaction, where first we react with base, and second we react with the electrophile. That will do the key alkyne addition reaction that we want to. And in a third step, we can remove the protecting group. We remove the protecting group with TBAF, tetrabutyl ammonium fluoride, and water. That deprotects our alcohol, restores the alcohol to its original functional group, and now we have made the product that we want. We just needed a 3-step protecting group strategy to do so. This is fine. This is good. We can do this kind of thing. Where you want to be aware and very cautious of protecting groups, though, is if the question wasn't a predict the product question, but if the question was a predict the reagent question. If instead I had worded this question this way, as they predict the reagent question, what reagents are needed to turn this starting material into this product, what I want you to notice, I mean, it seems obvious now that we've gone through it all, but if this were a question on an exam and this was all you had seen, what I want you to notice is there's no evidence the protecting group was ever here. There's no evidence that a protecting group was introduced and later removed. It's as if the protecting group was never there, which is kind of its point, but it makes these types of predict the reagent questions very difficult. We need to always be aware of the situation, situationally aware. We always need to be aware of our surroundings and not only focused on what we're trying to do, but what other functional groups may be in the way. So just be aware of this scenario, that if it's a predict the reagent question or a synthesis question, there may not be any evidence the protecting group was ever there, but you'll still need to be able to introduce the protecting group and take it away. This is an overview then of protecting groups for alcohols. Again, we'll learn a different protecting group strategy for aldehydes and ketones at a later time, but this is our protecting group for alcohols.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.